All right, so let's come back first. So for those questions online, I think I'll keep it, and then next time I'll get back to you because there are a lot. So yeah, let me do some arrangement. Okay, so let me quickly go through the how system code works, and then maybe we'll leave kind of 20 to 30 minutes for TA to talk about your assignment. So user space application somehow signal to the kernel, and then it runs a system call handler. And we'll talk about how to signal later. So there are two ways. Signal like this. There's things called software interrupt, or like people call them exceptions. So it's just like we'll put this kind of int 0x80, this kind of instruction in a register. Okay, so this is called the interrupt instructions. So when CPU execute these instructions, actually CPU will enter the system call handler. It will enter the kernel mode and run the system call handler. Okay, so like this. Oh, sorry. Switch it. Okay, sorry about it. Okay, so like this, just like there is a instruction called int 0x80, and then when executed this int 0x80, CPU will push another parameter called system call number to this EAX. Okay, so system call number will be linked with some system call handler, right? So just as our prior slides mentioned, for example, like this, system call 0 means the read and system call 1 means the write. Okay, so here the same things. If you put system call number 0 to EAX, then the kernel will go to check what the system call number is for inside the system call table. So if this is linked to the write operations, then kernel will run this system call handler, for example, the write handler to write something inside. Okay, so when you are going to send the system code to the Linux kernel, actually you need to not only to send this kind of interrupt instruction, but also the system call number to say like which kind of interrupt you are going to send. Okay. And then after running the system call, the same thing, you will be jump back to the user mode. Okay. Actually, system call and interrupt, they are very similar. So this is the reason why I put the interrupt instruction here, because system call you can think about it is a part of the concept of the interrupt. Okay. So it's just like CPU runs some spatial instruction to interrupt itself. So it is possible to run the kernel. Otherwise, if there are all user normal process, CPU cannot jump into the kernel. Okay. And I think next week, if we have some time, we can talk about interrupts. Okay. So how to implement a system call? The first one is the registration step. So to register a new system call to Linux, actually, you don't really need to worry about too many kind of details about how Linux works, because Linux helps to wrap up most of the things. Okay, so this is the user space. So in the user space, there are application and library. So the thing is, like, library is also part of the user space. So library is not in the kernel space. So libraries help to link the application and the kernel process. And then here comes the system call. So system call handler and system call, they are all in the kernel space. So your programming, I mean, you're going to add some system call, they are all inside the kernel space. So just like you need to do some programming on the Linux kernel, and then to add some like kernel-based C function. Oh, one thing is actually even kernel use C function and C library. It is quite different from the C you are using in the user program. Kernel has their own C library. Okay, so you need to follow kernel C programming. This is a little bit different from user process programming. Okay. Okay. So I think the procedure is quite naive. Just like you write a new system call, and the file probably will be look like this, system-hello.c. And this is the thing you write is the handler part, just like how you are going to handle this system call. Okay. So for example, if your homework just like to print hello world or something like that, then inside the system call, probably there's just only hello world like that. But for example, if you are going to write a more complex one, just like how to write the data to some file to some device, then the system call handler will become a little bit complex. And then after writing it, then you need to create a Mac file, and then you need to add something into the system call table, because you need to do the registration to let the Linux know you are going to add a new system call, right? So one thing you need is there are several parameters you need to add into the system call table. But actually, if you don't really understand each of them, it doesn't really matter, because inside the system call table, if you open it, there are already 500 something like template over there. So you can just copy the prior system call and then you can modify it to your own version. But let me quickly go through about what is each parameter means. So there's system call number. So as you know, it should be a unique number. So you need to check what is the, for example, maximum current number now, and just add 1, and you can register for a new system call. And then you need to choose which kind of model you are focusing on, like this kind of architecture, which kind of model, but you can just copy from the one in current system call table. So you don't really need to modify it. And then the system call name. So for example, what is the name for your system call? Like for example, system-hello, or like the write function, the read function, something like that. And then the program of system call, just like where you put your program in. So there are all templates there. So you can just directly copy the template and then do some modification. Okay. So this is about the system call. And then you need to add a new system call to the header file. So in the header file, actually there is something like include Linux system calls.h. So you need to put this system.hello, this kind of system call name in the header file for the system to link to the code. And finally, you need to compile, install, and update. So I think later on the TA will go through this part in a more specific way. Okay. So, because we still have some time, so let me briefly introduce interrupts, because I think there are some things that's similar to system calls here. So interrupts is quite important in our system, because in our system, there is not only CPU memory, there's things called peripheral device. So there is network device, there are storage device there, and there are usually several times slower than CPU. There are several orders slower than CPU. So CPU cannot wait for them always. So CPU needs some way to work with this slower hardware device. So there are 2 ways for CPU usually to work with this slower hardware device: the polling and interrupt. So polling means to periodically the kernel checks hardware status and response accordingly. So it means like CPU usually maybe 1 millisecond will come back to check the status for that hardware device. For example, if one day CPU is going to get the data from the storage device, and because the storage transmission takes a lot of time, so CPU probably maybe each 1 millisecond will come back to ask the storage device, hey, are you ready there? And this design actually, it consumes CPU resource, because each time when CPU comes back to ask the storage device, there is no other process can use this CPU core. Okay, so this is things like polling doesn't really do a good job on it, just like it wastes CPU resource, but it is more timely. I mean, if it is regular, actually, CPU can pick a better time to check it. And there is another thing is called interrupt. So interrupt is to let the hardware to signal to the kernel. Just like if the hardware is ready, I mean, if the storage device thinks like, hey, it is ready for a CPU to access the data, then the storage device will interrupt the CPU. So CPU probably will be stopped and then to do some things. But like if there are some process they are running now, that process will be stopped, because usually interrupts is high priority process. Usually it has the highest priority, so it can interrupt most of the process there. Okay. So what causes interrupts? So there are several there are several ways to send the interrupts, but usually interrupt you can think about is how a device physically produce electronic signals to the systems. So which are directed into input pins on an interrupt controller. So you can think about, because when you block the keyboard, when you block the mouse, the storage device like SSD hard disk drive in your motherboard actually, and each time when you are going, when the device is going to send the interrupt, they will use the electronic signal to send this kind of interrupt to interrupt CPU. Okay. So I have a toy example here. So here is, okay. So here is a motherboard actually. So on the motherboard there are CPU, right? Because our CPU chips that are say on the motherboard, and usually there are things called north bridge and south bridge. So primarily, north bridge is for memory controller hub, and south bridge is for I/O controller. So you can think about north bridge. Usually, they are designed for the faster device like DRAM and GPU, and south bridge they are usually connected to keyboard, hard disk, SSD. They are usually slower. Okay. Oh, sorry. Actually, people are saying about north bridge plus south bridge is called a chipset. Okay. Okay. So when the storage device like keyboard, hard disk drive, PCI, SSD, they're going to send the interrupt to the CPU. Actually, there is an interrupt controller on the south bridge. So the control you can think about is a specialized like CPU. They're going to do something. So the signal will be sent to the CPU via this kind of interrupt controller, and then to send to the interrupt controller on the CPU, so CPU can do something. Okay, so there is a thing as actually after 2019, all north bridge functions has been integrated into the CPU. So actually there is no north bridge in modern like motherboard now, but south bridge is still there because south bridge is used to connect with the storage device. Okay, just want to let you know. So when we talk about interrupts, actually there is another thing called exceptions. So exceptions are produced by the processor while executing instruction either in response to a program error or abnormal condition. So you can see actually system code is in this category, abnormal condition. So what we mean abnormal condition usually is like when the user process is going to interact with the hardware device. So in this case, actually, processor will will run the interrupt itself. So this is called software interrupt. I mean, there is no hardware electronic signal to send to the CPU, but CPU itself will interrupt itself. Okay. So there are two ways to I would say like there are two ways to do the interrupt. One is from device to notify the CPU. The other is CPU, like processors will interrupt themselves. Okay. Okay, so why I usually say like system code and interrupt, they are very similar, because if you still remember in the system code, there is a system code number, right? And there will be a unique number, and interrupt is the same things. So each device, when they are going to send the interrupt, before that, they need to do the registration. So actually in current interrupt design, the interrupt request, the maximum of the interrupt request is 256. Okay, I mean there do have some way to extend this number, but normally there are 256 interrupt values there. So when each time you are going to insert a peripheral device in the systems, you need to register this interrupt. Okay. So for each specific interrupt is associated with a specific device, and the kernel already knows it, because most of the things they are assigned during the boot. Okay. So for example, just like IRQ0 usually means a timer interrupt. IRQ1 usually means a keyboard interrupt. Okay. So, I mean, there are also some dynamically allocated IRQ numbers. For example, if you plug your PCIe device or a SATA device in a deep system now, actually you don't need to reboot the systems, and that is because actually currently there are some dynamically allocation technique here help to register the interrupt dynamically. Okay, so this table is just going to let you know actually there are some already there are some interrupts when you do the booting. So the left-hand side is the default processor interrupt vector number. Okay, so each processor they have their own definition there. So when you set up the BIOS, when the BIOS is up, actually the BIOS will help to register some of it. So for example, IRQ0 is timer, is a system timer. You can think about timer interrupt. IRQ1 is the keyboard interrupt, right? But if maybe you can find like there are some overlap between the processor original one and then the the BIOS register one. So in the operating system, there will be remapped. So you can see like operating system will remap it, this kind of blue part to here. So we call them master PIC and slave PIC. But I mean, they're just a name. You can think about master PIC, just all those kind of IRQ0 to IRQ7. They are master PIC, and slave PIC, they are from IRQ add to IRQ 15. Okay, but the same things in the exam, we will not ask you to draw these kind of things. I mean, you just need to know, hey, there is interrupt vector number for each interrupt there. Okay. Okay, so I think I will let the TA to take over first, and then maybe next week we can start from this interrupt, how interrupt works. Okay, so